So I'll go again. Lovely. Hi. Yes, my name is Courtney. Today I'm going to talk to you about hydrogen-deficient carbon stars, and the tagline, of course, being what happens after a white dwarf merger, which probably many of us are interested in. So let's go right in. I want to start by highlighting the group that I work with. Generally, these are the people that I work most closely with very often. Jeff Clayton, myself, Ashley, who's here, Evo, Jamie, who's also here, and Patrick, who's here. There's actually like a really cute little HTC hub in Canberra, which I find really fun because, like, say Patrick actually did his postdoc here at ANU. There are quite a few other people in Canberra who've studied HTC stars, which I find cool. So we start with our picture of a typical star's evolution. This is what we have in our mind when we think about a stellar evolution. And we tend to think of having the massive stars here on the left and at the top. We think of the low mass stars being over here, sort of in this more cool regime. And what if I told you that we had found a star right around here up with the supergiants that was only about 0.8 solar masses? You would probably say that was a really weird star, and you'd be right. So what that is an HDC, and that is where we find the HDCs. So HDCs, or hydrogen-deficient carbon stars, are a rare type of low mass supergiant star with very peculiar abundances. So they have a number of abundance peculiarities, but the main ones are the titular ones. They're hydrogen deficient, so they have less than 1% hydrogen by mass, as opposed to a typical star, which has 75% hydrogen by mass. They're also carbon rich, so they don't have any oxide bands in their spectra. They tend to have carbon molecular spectra. They also show partial helium burning products, which are oxygen 18 and 19F. And I will come back to these as well and explain what partial helium burning is, but that one is really important. They also have weak C13 and strong S-process material on their surface, which is really interesting as well. So let's look at a typical HDC spectrum. If you've never seen a stellar spectrum before, don't worry about it too much because I will walk through these. But here on the left, we have a warm HDC, which is around F type. And we have a cool HDC, which is around K type, just to anchor yourself a little bit. So to give us an idea of where we are, we have the typical suspects, calcium-2, H and K, and a calcium-2 triplet. So we're right smack dab in the middle of the optical wavelengths here, okay? However, these are hydrogen deficient stars. So for the warm star, which is around F type, we expect to see a Balmer jump, and we do not. We also don't see any H alpha or the Balmer series as well. In the cool stars, again, we don't see an H alpha. We also don't see that CH band. Remember, we should be seeing the G band around these types of temperatures. We don't see that either. So this is really weird when you see these kind of spectra and you don't see any hydrogen features at all. There are also carbon stars, as I mentioned. So for the warm stars, we do even have a very weak C2 band, even though it's a bit more like a C2 divot. But over here for the cool stars, we have an absolutely rich carbon molecular spectra, with all these C2 bands here in the blue and the CN bands predominantly in the red. So these are our carbon stars. And just for posterity, we can actually see, if we look really closely, that strontium-2 line from the S process here in this cold star as well, which is really good. Cool. So this is what a typical HDC spectrum looks like. Just if you've never seen one before, you can see just how weird they are if you're used to stellar spectra. There are two types of HDC stars. The famous one is the dust-producing one. Those are the R Corona Borealis variables. If you know of HDCs, you probably know of these guys. These are known for their irregular asymmetric declines of up to 8 magnitudes. Here on the left is the spectrum of the prototype R-core Bohr over the time from 1989 to 2017. And just for reference, I know this is a little hard to read. So up here is 6 mag, and at the bottom here, 16 mag. So that's about 8 magnitudes of a decline. And in fact, this bigger decline here is about 11 years long as well. So they're also super irregular. They're asymmetric. We have no way of predicting them. But we also see these variations at maximum light, which may or may not be some kind of pulsation. We also have the dustless type, which we're calling the dustless HDC stars. And historically, they were just called HDC stars. So that gets a little confusing because R-core Bohrs are also HDCs. So these are the dustless type. So they have identical spectra. They have max light variations, but no declines, no dust declines as well. So what forms these stars? I've given you a big hint with the title of this. But one big clue, the clue that led us down this path, was this really weird isotope, oxygen-18. So oxygen-18 is a rare isotope. Oxygen-16/18 ratio in the sun is about 500, whereas in these stars, the oxygen-16 to 18 ratio is about 1. And so that means we have about 500 times more oxygen-18 in these types of stars than in a typical star. So this isotope is rare because it indicates something called partial helium burning, which I will again get to a bit later. And this is possible through a white dwarf merger, which is one of the big reasons that we decided to go down modeling the stars this way and showing that they could be from white dwarf mergers. Here on the right, I have a sample of some HDC star infrared spectra, where you can actually see the oxygen-18 band right here next to the oxygen-16 band. So these are the CO bands in infrared.
Is that for one razor?
And not two of them. So this is our big smoking gun towards the white dwarf merger hypothesis. So let's talk about white dwarf mergers a bit in general. They have a range of masses at which they can occur. This is a really awesome figure. We have the donor mass here and the accretor mass as well on the x-axis. Here in the middle is the Q = 1 line. And here in this line is for the total mass of 1.4 solar masses. Yeah, what's up?
Can I just, when you're talking about white dwarf mergers, you're talking about 2 white dwarfs merging?
Yes.
White dwarf so it's one of
yep, yes. So up here on this side, we have the high mass regime of 2 white dwarfs merging, double white dwarf mergers, where you have things that are explosive, so type 1a supernovae, core collapse supernovae, things like that. But lower than 1.4 total solar masses, you don't really expect those to explode, and those post-merger remnants could possibly persist. And so we think actually that the archobores and HDCs are right around here in that in this region of masses. So we tend to think of HDCs being so-called a low mass counterpart to the type 1a supernova. You can get even smaller post-merger remnants as well, perhaps. So our schematic of what we're looking at here, the merger scenario, our typical low mass white dwarf merger that we're thinking of is a helium white dwarf around 0.25-ish solar masses and a carbon oxygen white dwarf around 0.5-ish solar masses. As those in spiral, what happens is the helium white dwarf gets tidally disrupted, it mixes up, and it forms essentially an envelope around the carbon oxygen white dwarf, which is mostly untouched. So that carbon oxygen white dwarf kind of just sits there, and the helium white dwarf forms an envelope around that star. And then we have a really hot shell that's burning helium right near the surface of that carbon oxygen white dwarf, which serves like a typical helium shell burning. And we have this really extended envelope out here. So the structure that we want to keep in mind as we move forward is that our star has an isothermal core, a hot helium burning shell just outside of that, and an extended envelope. This is coming from a 3D simulation of this particular merger process. So we've gone ahead and modeled this process to see, can we actually make an archobore with the right abundances and the right temperature and luminosity? And we've done this in 2 ways. Both ways use the stellar evolution code MESA, which is the 1D evolution code. One way is the stellar engineering, and as the name suggests, it has a lot of engineering. We first create a star in MESA that has a degenerate core. That's how we set our total mass that we care about. And then we change everything about that star. We change its abundances, we change its entropy profile, and MESA has built-in mechanisms for you to do this. Once you've done this, then you can turn all the physics back on, and you can evolve that star in 1 dimension. We've done that in 3 papers so far, and in fact, we still do this because it's a bit of a simpler process than the other one being 3D to 1D mapping. So for this one, we take an actual 3D hydrodynamical white dwarf merger, and we spherically average that 3D model into 1D, and then we evolve that in MESA as well. So we've done both of these, and both of them show very good results. So here's here's the T-row profile of these 2 models. So T-row profiles are really useful in stellar engineering, or sorry, in MESA modeling, if you ever look at stellar evolution. But if you're not familiar with them, what we're looking for again is that isothermal core, hot shell, and extended envelope. So we have that in both of these models. Here's the still engineered model and the 3D model, where we have this isothermal core, we have a hot shell on top of that that's helium burning, and then we have an outer extended envelope. Okay, same deal with the 3D to 1D. We still have an isothermal core. We have a helium burning shell just on top of that, and an extended envelope. Okay, so the 3D to 1D mapped models obviously have more structure. That is because they are a much more complicated process to create, and they come directly from 3D, whereas this is a much more simplified model. And they both work just about the same, but obviously this one has its limitation. Okay, so then we evolve these post-merger objects, as I mentioned. So what happens is this hot helium burning shell acts just like shell burning on the red giant branch. And so this star evolves straight up what looks like sort of the AGB, RGB-ish region. It evolves upwards as that hot shell pushes on the outside layers of the star. And it evolves up to where this box is. So this box is the approximate range of observed stars in temperature and luminosity space of observed HTC stars. So getting in that box is a good sign. Up here at the corner is what we call the HGC phase. This is where the model spends most of its lifetime. And that's where we think we would be most likely to observe this star if we were to actually observe it. So that's really good. Once it's done there, it starts to lose mass and it evolves leftward, sort of across the HR diagram, and turns again into a white dwarf. And so this is what we think the merger process is looking like. For the record, this model here is the 3D to 1D model, and all of this stuff here is probably numerical. It is occurring on things like 2 years, which are not really physical instead of lifetimes. So they're probably numerical MESA things. Lovely. So we've recreated the temperature and the luminosity, but that doesn't mean a whole lot. For the record, we are able to reproduce the abundances quite well. But one thing we were really looking at when we did these models was to explain oxygen 18, right? So I said oxygen 18 can happen in white dwarf mergers, and we wanted to show that that was possible. So partial helium burning is basically kind of what it sounds like. You have this alpha capture reaction chain, which goes 14N into oxygen 18 into 22 neon, right? Generally, in a typical star, you're going to do this whole alpha capture reaction chain. But in these stars, or in partial helium burning, what has to happen is you have to interrupt your alpha capture reaction chain for some reason or other. And the reason we think this happens in all of our models, the stellar engineered and the 3D to 1D models, is that we have this mixing structure, which looks like a fully convective envelope, but only until about 10-ish years of star lifetime. And in fact, the convective region here only communicates with this burning shell, which is here, this red part. It only is able to communicate with this burning shell up until about 100 years of stellar evolution. And this is consistent across all of our models. After that point, the convective region splits away from the burning region, and you can never take those burning products up to the surface of the star anymore. And so basically, we're only seeing helium burning for 100 years in these stars. And so that's why we think we have oxygen 18. And in fact, if you have hotter models, for example, you can change this mixing profile and you can get more 22 neon or less oxygen 18, things like that. So that's really good. Our models have shown at least that we can reproduce this oxygen 18 in a post-merger type model, which is really good. I'm going to take a brief aside to mention 2 other related stellar classes. These are the DY-PERS, which will be over here, sort of to the cooler part and slightly less luminous than the HDC stars, and the extreme helium stars, which are going to be brighter and hotter. Okay. In the HR diagram, basically where they would be is that the extreme helium stars are found in this region, sort of where this star would move leftward through the extreme helium star region. And the DY-PERS would be something like a cooler cousin. We're working on these a little bit. I'm not going to talk about these a whole lot. If you're interested, please ask me, but you will see allusions to them on some of my plots later. So I wanted you to know what they were. Okay, so I've talked about mergers. Let's talk a little bit about kinematics. Post-merger stars have to live in old star populations, right? You have to go through 2 stellar lifetimes and then evolve into a new star after that. And we can already tell that these stars are living in old star regions from their right ascension and declination. That's pretty good. We also know that these are low metallicity stars, which is yet another indication of them being old. Here's the projection of what they look like in 3D space, just with the known archivores. But luckily, there's a whole mission designed to tell us where stars are, so we can get a better idea of where exactly these stars are. But there's actually a problem, which is that Gaia really struggles with the HDC stars. So we have to remember that archivores specifically, these are the dusty ones, these have dust declines. And those have strong color changes and strong brightness changes. So the first thing we have to be careful with is that Gaia quotes an average G magnitude. So if your star has a decline during Gaia's observation, you will have a biased G magnitude. So if you look at this color magnitude diagram for Gaia here of the HDC stars, you might think there's sort of 2 distributions almost, right? But that's not exactly true. When we look at the difference in the maximum Gmag and the minimum Gmag, we can get an idea of if the star has gone into decline, because typically we don't have 8 magnitudes of variation. And you can see actually that this separate little section down here is all declines. And so all of these stars, their G magnitudes are biased by this decline process. Whereas probably the real distribution is this up here. We have one other issue with the archivores, which is that Gaia's PSF has a chromatic effect. So dust declines also create color effects in your star. And the PSF changes in Gaia when you change color significantly. And so this can also lead to bad astrometric fits if your archivore goes into decline. So you have to be really careful. This is a plot of 2 Gaia fit parameters, one being the RUI, the renormalized unit weight error, and this one being some more complicated error value of the IPD, where basically what you want to keep in mind is that this part is bad and this part is bad, and so this part is really bad. But basically, these stars, the blue ones, are the ones that have gone into decline at some point during the observations. And so all the stars that have gone into declines, their astrometric fits are also not very good in Gaia. So we have to be really careful when we use this data. But that being said, we've been able to do some stuff with it. And what can Gaia tell us? It can tell us a couple of things. Big thing is that we already knew this, but we're only seeing this side of the galaxy still. So here's the galactic X and Y. You can see the sun being here. We're sort of looking at a cone around the galactic center, and here's the galactic center itself. We already knew that we weren't seeing onto the other side of the galaxy with Gaia. So this is a good representation of that. Another thing that we notice is that if we plot their space velocities, we'd see HDC stars in all of the regions. We see HDC stars in the halo regions, the thin disk, and the thick disk regions. And so that's actually really interesting because we don't necessarily expect them to form in all these different regions. How are they in all of them? So we have a lot of further discussion in our upcoming paper that we're writing right now about all of this. But what's really interesting is just that we're seeing HDC stars in a lot more kinematic regions than we originally expected. Okay, let's talk a little bit about dust production as well. So the archivore stars, the dusty ones, have really interesting dust. They're not all the same either. So here I have just 4 well-known archivores, where you can see that their, what are these, like 20, 30-year light curves are all very different. You have some stars which have these very long extended declines. You have some stars which have lots of really fast declines. You have some stars which are sort of in the middle of those two. And then you have some stars like this one, XXCAM, which has not had a decline for almost 200 years, which is really interesting. And so not all of our stars are the same, but we can think about the geometry. This slide. Okay, so we also can look in the infrared to see these dust shells. So we can look at the differences between all of these dust shells through the archivores. And here's an example of just 3 from a paper by Edmond Thiel in 2018, These are the infrared dust shells around SU Tau here, RY Sag, a very famous archrobore, and then the prototype Arc Borealis itself. Where you can see in something like SU Tau, you have this really weird dust structure where it almost looks like a bow shock, but we don't actually know why this dust is only forming on, say, one side of the star. We have RY Sag, which has a very diffuse looking dust shell around it. We have Archrobore, which has something that it almost looks a bit more clumpy than the other ones, than RY Sag in particular. And so this paper uses these infrared dust shells to measure the dust masses, temperatures, and velocities of these stars. However, this has only been possible for the closest and brightest Arc Borealis stars, because they're the only ones that have these infrared, that we're able to resolve on the sky with this infrared observations. So after a lot of dust work, we have an idea of what we think the geometry is. So you might at first be tempted to think that it's a bunch of clumps of dust which are perhaps orbiting the star. But in that case, you would see something periodic, or at least close to periodic. But in fact, what we actually think the geometry is something more like, since this star is supergiant, it should be rotating very slowly. And what happens is the dust actually forms on the surface of the star, pretty close to it, in a little clump. And that clump moves towards us in our line of sight and sort of expands to slowly cover the entire star. And eventually it becomes diffuse enough that it disperses and we're able to see the star again. And so typically this is the idea of what we think the geometry of these is going to look like. There's a paper from 2007 that I am really interested in, which claims that for RY Sag and 5 other stars, that the onsets of these declines, of these dust production events, are tied to a period. Now, that doesn't mean that, for example, they're going to have a decline every 40 days. What that means is that the declines can happen only every 40 days, if that makes any sense. Not every 40 days, but on only 40-day periods. And that was done with this light curve and a couple of others. Something I'm working on right now is to extend this work to all of the known Archrobore stars with all of the plethora of light curves that we have these days. So that's a work in progress, but this is, if it's true, this would imply that the dust might be tied to some pulsation frequency within the star, which would be quite interesting, because how would the dust know about that pulsation frequency? Is that pulsation frequency even associated with an oscillation in the star? These are all open questions and things that we're thinking about a lot these days. Okay, so I've mentioned pulsations. Let's talk about them. So HDC stars are known to have variations at max light, which have periods of around 40 days that seem to change fairly often. Some stars are a bit more regular than others in their period. Some stars you can actually measure something like a period, and some stars, every time you come back to measure it, you measure a different period. They also have the amplitudes in their variations of around 0.2 mag on average. Some of them get up to about 0.5 mag, but usually not much more than that. And as I said, some are known to be more regular than others. This is a AAVSO light curve of Arc Borealis for the past, I want to say like 2 years or so. And so we're actually really well studied by AAVSO, which is really nice for the prototype star. And you can see, perhaps even just by eye, that if you were to estimate a period, you would probably change that period depending on if you measured this part or this part here. We probably measured different periods in those times. So there's discourse. It's kind of not been looked at very much recently, but are these oscillations or are they something else? So the difference being that you can have in a star a pulsation, which is the actual physical size changing of your star. Something is changing in your actual star. And those can look like radial pulsations, like this animation here, where you actually change the radial size of your star, or they can look a bit more non-radial like these, which are a bit more like more complicated oscillation profile. Or it could be something a bit more like granulation. So on things like the sun, this is an actual GIF of the sun's surface. If you have a convective surface, what you end up getting is convective cells. And as those convective cells move up and down, you change your brightnesses. And what that looks like in the star, it looks like a variation of some kind, but it's not periodic. It has a completely stochastic nature. And so there's a lot of discussion on what this could be, if it's pulsations or if it's granulation. The other thing is that it could be both. So solar-like oscillators are a thing that I study now at UCID. They have both granulation and pulsations. So for the record, it can be both. And in fact, in solar-like oscillators, the convection on the surface is what drives the pulsations, the oscillations. So it's really interesting to think about which exactly this could be. Now, no one has studied this systematically, but actually there's been evidence for both of these. Here on the left, I have some radial velocity pulsation phase-folded light curves for 5 different arcobores, very bright arcobores. We can see very clear pulsation structure. These look just like any other typical oscillator that's, something like a Cepheid. It has a light curve very similar to this. And so this is one, tick towards, these could be truly pulsations. However, we've also seen evidence of stochastic variations in extreme helium stars. Now remember, these aren't arcobores, but they're presumed to be similar. And with test data recently, Simon Jeffrey showed that something like this cooler EHE star is showing extremely stochastic variations. So basically, what they've done here is taken this half of the light curve and this half of the light curve, and they have done a Fourier transform on both of them. And what they're seeing is that the signals are not coherent. The signals are entirely different. And so that's your signal of stochastically excited variations. And so for the extreme helium stars, at least, they've shown that they do at least have these stochastic variations as well. Okay, so my closing remarks. I hope that you guys think HGC stars are interesting. My goal here was to get you interested in these stars and to leave you with a lot of open questions, because we have a lot more questions about these stars than we do answers. Our big questions right now that we're working on are HDCs related to the extreme helium stars and the DY-PERS? I, in fact, have an honor student working on DY-PERS right now that I'd love to tell you about. What galaxy population are HDCs from? Are they formed in one population and then maybe kicked out in some way, since these are merger products? Big question, are dust declines pseudo-regular? Because if so, that's really interesting. And if they are they tied to a pulsation period? Extension of that question, do HDC stars actually have a pulsation period, or is it completely stochastic? We don't know the answers to any of these. But if you are interested in working with us to answer these questions, or you're really interested in them, I would love to talk to you, and I'll be here all day. We have a cool shirt too. So version 2 is coming soon, probably. I think, do you have one?
I was gonna ask if you can get me one, because I still haven't been able to get one.
I don't even have one, but Patrick for sure has one. So if you want version 2 with the updated spectral classification, let me know. And maybe we can get an order going. That'll be cool. Anyways, thank you guys so much for listening today.
All right, we'll take questions. Gary.
Just go back one slide. I was quite intrigued that the 5 examples you showed there all have periods very close to 40 days.
Yes.
One of them. So is that sort of a smoking gun that there really is a 40-day?
It's possible. So this, of all of the historical papers which study pulsations in HDC stars, they all claim periods around 40 days for every star that's been studied. I don't know. I mean, surely, yes, this is an indication that there is something in these stars that's at least happening around a period of 40 days.
So what is it that produces a period of around 40 days? Is that just the sign of stars?
So I know.
Rain from heaven. Someone got the joke. Okay, sorry. Go
Oh,
on.
you're good. I know at least in solar-like oscillators that the pulsation frequency of the most power is related to the radius. It's also related to things like the temperature, things like that. And so I would presume that that's possible, that it is indeed related to the radius of the star. And I think if you do a back of the envelope calculation of just the expected pulsation period based on the radius and the luminosity, you do get something like 40 days as well. So that is, yeah, a very good indication that it could be this. But we just haven't, the problem that we're having right now is that there's all these really lovely long-term monitoring light curve things like Kepler and TESS is what I'm going for here. But all of those things remove long period variations. That's our problem right now. And the other thing is we do not have a single HDC star in the Kepler field. So we don't have any Fourier light curves for these stars. So things like TESS, they tend to really just take out all of our signal. And so you have to do a lot more complicated stuff like that. So our big problem right now is having a long enough baseline to actually measure a period that's stable for longer than 2 pulsation phases, which would be around 40 days. Does that make sense? Yeah.
Mike.
Are they lying in the instability strip, in the helium instability strip, or are they scattered?
I have not checked. But that's a thing that once I actually get to doing a pulsation paper, which is my plan after the paper I'm working on right now, then certainly that is something that I will look into. But yeah, if they were in the helium instability strip, that would be, you know, very obvious as to what could be causing this. Yeah.
Are there any long-term monitoring missions in the future that might help in kind of answering these questions?
So things, I know Roman is a big one. Roman is looking at the galactic bulge, which is really nice. However, Roman is observing for things like 20-day cycles. But I think they're looking at possibly doing Kepler-like sections on 2 other sides. I saw this at the recent CASC meeting that I was at, where they're thinking about also having something kind of like Kepler in a different field as well. So TBD, right now we're using Atlas, and Atlas is actually pretty good if your star isn't too bright. And Assassin can also be really useful as well. For Archer-Bohr, you could probably just use AAVSO, considering how well studied that star is.
I think there was a question online.
No, there wasn't. I checked. It was, or unless one has appeared in the last few seconds.
Flashed up down there.
Oh, did it? Okay, I'm sorry, I missed it.
And so Simon.
Yes, okay. So Simon Campbell asks, is Ogle useful for these stars?
Yes, we actually have a monitoring site for Ogle. And I think we discovered a bunch of Archer-Bohrs using Ogle in the Magellanic Clouds. So yes, that is also useful. It's just a matter of taking all of these light curve sources and putting them together and getting one big data set for the stars and really seeing if that stuff is coherent across long baselines.
All right, we have another online question. Mark Dure, I'm not quite sure how to pronounce it. Please go ahead and ask your question. We'll hear it in the room.
No worries. Thank you very much. Just a question on the kinematics. The formation of these white dwarf pairs, do they involve supernovas at all? And would the scattering of there be a possible scattering into the thin and the thick disk? And also, would that be a solution for your SU Tauri thing, that actually might be a high-speed star and actually is forming a bow shock of some sort?
Yeah, it's possible that they have been ejected from triple systems in some way. As far as they have any explosive nature like in their system, that's probably a question a bit more for Ashley.
I would say not.
Okay, she says no, that's probably not. Ashley being the expert on our population synthesis for these types of stars. But yeah, if indeed SU tau was moving really fast through the galaxy, that would be a pretty good reason for it to have something that looks like a bow shock for sure. I just don't think we have any good estimates of, say, how many stars have been ejected from systems per se. But yeah, good question.
Mike. So for Arcobore stars, the ejection of these dust shells is strongly related to metallicity in the outer shell.
Yes.
So what determines the metallicity in the outer shell? Is it basically just the helium star being mixed up due to convection after merger?
Yeah.
Or is there anything else?
At least so how we handle this in the models is that we assume the helium white dwarf envelope is fully mixed. And so the metallicity of your star, your Arcobore, would just be the metallicity of your helium white dwarf. If that is physical, different question, but that's how we handle it in our models. And at least based on these, it depends on how efficient this mixing is, but you could assume that some mixing might get pulled up from there. You might even have dredge up from your carbon oxygen white dwarf as well. But generally we interpret the metallicity as being the metallicity of the progenitor stars.
Related to this, so because you showed a nice summary of your MESA simulation and how you can infer oxygen 18 ratio from this, and this is really cool. I just was wondering about, do you have a grid of models? Or
yes.
Yeah, so and do you notice any significant differences in terms of your abundance ratios depending on the initial masses of those white dwarfs you start with, the helium or the carbon oxygen, or
okay.
I don't know how large a grid is.
So our grid is 18 models. It has 9 different helium burning shell temperatures and 2 different metallicities, being 10% and 1% solar. Or being 10% solar and solar. Solar. Yeah. 1% solar is really hard to run in MESA. So that's the grid that we have for this paper. My student who's working on DY per stars is trying to do lower mass mergers. And so we do have some preliminary results on that. We haven't looked at these merger profiles, but we have looked at just the temperature and luminosity location, at least. And then as we sort of progress through the end of that honors project, we'll start looking at things like this mixing profile and the abundances. But yeah, we have some preliminary stuff, but it's something we're working on, is changing the total mass and then the mass ratio as well. That's a really interesting question for us.
All right, I think there's a question online. Simon, do you want to go ahead and ask your question? You can unmute.
Yeah, thanks for the very nice talk, Courtney. My question is, so you have oxygen 18 sort of explained here, which is great. And you mentioned there's S process observed as well.
Yes.
Are you getting neutrons in these simulations?
Yeah, so I have a paper on this, on S-processed stars. I think I have a backup slide on this as well. Let me just see if I can get to it. Please? Okay. I think I have one. Just showing I have a lot of backup slides, you guys. Okay, no, I lied. Okay, so I have a paper on this, which is where we identify 6 Arcobore stars, HDC stars that have really, really strong strontium lines and really strong barium lines in their spectra. And within that paper, what I do is I take the model from this model here, and I calculate the potential neutron exposure based on the model itself. So MESA tracks neutrons as well. It also tracks C13, which is where we think that neutron comes from. So I have a paper where I've done that. I think the conclusion was that we cannot explain the necessary neutron exposure so far just using one of these models. And Another side note is that for this 3D to 1D model, Brad Munson also used NuGrid. So what NuGrid is the post-processing addition to Mesa. So it takes the output from Mesa and does a lot more nucleosynthesis afterwards on the side. And he used that to try to calculate the exact S-processed material that you would see on the surface. And he still couldn't exactly explain why we have so much S-processed material on certain HCC stars. So we've looked at this quite a bit, but as of right now, we can't explain how much S-processed material we see. We can explain some, but not all of it.
Interesting, thanks.
Yeah.
Your questions. I'll ask one. Can you go back to your Kippenon diagram? And
Everyone
I'm
loves this.
just curious, what is shutting off the convection? What's the physical mechanism that's making the convection cease?
I do not know. Yeah, I haven't. I did this when I was in my PhD, so I haven't looked at it again recently, but certainly with having my student working on these models again, it's something that I'm thinking about and looking at in more recently. But as of right now, I have no real reason, no explanation for why the burning regions split, and also why it completely disconnects from the burning shell itself.
All right, Jonah.
If you go to your nice GIF of the dust coming off of the
I made that by hand, for the record. I drew it.
Wonderful. So the dust is all coming off of kind of one part of the star.
Yep.
Do we have any idea of what kind of mechanism might be causing that?
No. So Jeff Clayton, my PhD supervisor, is the dust guy of these stars. There is one paper where they question, could this be a sunspot, like a star spot, where basically that part gets cool and then you would form dust there and then it would get pushed away. I don't know if they were able to say, yes, this is happening, or if they were just like, could be. There's a paper on that. And then there are some papers showing that the dust is not spherically symmetric. So it's like a polarimetry type paper where you can see actually the symmetry of these, and they find that they're not actually presumed to be spherically symmetric. So we do think it's clumpy of some kind, but what's actually producing the dust and pushing it away, we don't really know. Yeah, and I think the last dust like study of that kind was at least 15 years ago.
There is a raised hand online. Simon again? Or is your hand still just up from last time?
No, just on this one. So we've got a student working on S-type stars and they've got similar light curves to what you're showing, and it's all over the place as well. And we're trying to go through similar sort of theories about what it could be. And one of them that came up was this as well. And there are actually 3D simulations of giant star convection. It's by Freytag et al. And what we see is that the convective cells are about a similar size to the star. So this may not be so crazy. I can post the link to the videos. He's made some nice videos in the chat there. Don't know if that's useful. Yeah, but Yoshi Mori is working on this, and he's looking at all these light curves, Assassin, Ogul, everything as well. So it might be good to...
surely if we look at things like those dusty upper HEV stars, we might see some similarities with these types of systems for sure.
Yeah, there's a lot of overlap.
Yeah, definitely.
All right, I think, any last questions? All right, well then I think let's thank the speaker again. We'll arrange lunch.
Yes, arrange lunch. So as usual, you know, let's meet at 1 o'clock outside for those.
1 o'clock?
Yeah.
Okay.
10 minutes from now, is it?
Sorry, do you mean 12 o'clock? 10 minutes from now would be 12 o'clock.
Oh, 12, sorry, yeah, 12.
That's why I was confused.
Well.
12 o'clock, sounds good. Thank you all so much.
Thank you.
Thank you.
Dude. Centers of excellence, let's talk. How was your